Okay, let's take a look at this ALEKS problem, which is called calculating the wavelength of a spectral line from an energy diagram. Okay. This energy diagram shows the allowed energy levels of an electron in a certain atom. Note that the SI unit prefix zepto means 10 to the minus 21, and you can find the meaning of any SI prefix in the ALEKS data tab. So take a look at the energy diagram. Is the arrow pointing up or down? It's pointing up, right? The red arrow is pointing up. If it's pointing up, that means this is a process of increasing energy. Increasing energy is absorption. Think of it like a sponge. What happens to the weight of a sponge when it absorbs water? It increases, right? If you squeeze the water out, it decreases. The similar phenomenon here. The energy of an atom increases when it absorbs the energy of a photon. So the electron is moving up, and that's absorption. So the third question here, which says, if the electron makes the transition shown by the red arrow from A to C, will a photon be absorbed or emitted? It will be absorbed. Of course, if the arrow is pointing downward, then that would be emission. Try to remember what the physical process is. The arrow is representing what happens to the electron in the atom. So you've got this nucleus. The nucleus is positively charged. You've got this electron, which is negatively charged. If a photon comes in, the photon has energy, right? Photons have energy. We know that. The energy of a photon is hc over lambda. Okay? Or h nu. H times the frequency. So that's energy is going to be transferred into the electron, and then the electron will move up to a higher energy. Okay, so the electron moves up here. That's absorption. Emission is the opposite. When the electron comes down from a higher level to a lower level, that's emission. Okay, so we've got that taken care of. Now, what is the energy of the electron in the ground state? So let's do that first calculation from A to C. And the first question is the energy of the ground state. Now, the ground state for the hydrogen atom, this says atom, but we're really doing this calculation for a hydrogen atom, to be honest with you. So it's the ground state. The ground state is the case where n equals 1, the lowest possible level. There is no n equals 0 in electronic states of an atom. It's either n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You cannot have fractions or decimal numbers. You cannot have negative numbers. You cannot have 0. So it starts at 1. So A, the ground state is A. We're going to take a look at that energy level. That energy level is right there. You can see where it's at. It's at between 400 and 600. So here's 400, here's 600. It looks like there's one. Let's see if I can bring this up here. There's 1, 2, 3, 4 sections there. So it looks like it's going up 40, right? 400, 440, 480. Oops, nope, I think that's wrong. Let's do 440, 80, 20, so I'm off a little bit. So let's try 450, 500, 550, 600. So it's going up 50 zeptojoules each one. So it looks like it's the first one above the 400. So that's 450. So the energy at A is 450 zeptojoules. So this actually could be any atom. It doesn't necessarily have to be the hydrogen atom. Okay. Now it says, what is the energy of the electron in the first excited state? Well, the first excited state is B. Let's see if this goes up there. So B is right there. And it looks like it's up 2 notches from the 800. So that would be 900 zeptojoules. That's not bad. So we have those two energies. That's all it's asking for those first two questions is what are those energies. Now it does have another more involved calculation. It says calculate the wavelength of the photon that would be absorbed or emitted. Round your answer to 3 sig figs. Well, we've already decided it's going to be absorbed. So here's how you find the wavelength. First, you calculate the difference in energy. The difference in energy is the final energy. Now since the arrow is pointing upward, I went up to B. I'm sorry. It's actually going up to C. So it's 1,000. C is 1,000. I thought it said B. I'm sorry. So this is C. So let's erase all of that. If you saw that, it's probably driving you crazy. So delta E would be the final minus the initial. So that would be 1,000 zeptojoules minus 450 zeptojoules. So that's going to be 550 zeptojoules. Right? Just take the difference in the two. Final minus initial. Now, we got to convert that to nanometers. That's wavelength. So here's what I'm going to do. I'm going to put this energy just in joules, just to make it easier for ourselves. Zepto is 10 to the minus 21. So 550 times 10 to the minus 21 joules. There's your delta E. That's not bad. Now let's do our delta E is hc over lambda. That's the relationship between energy change in an atom and the wavelength of the photon that's absorbed or emitted, but in this case absorbed. Let's do our algebra. Multiply both sides by lambda. Okay, so that gives us just hc on the right side, right? Divide both sides by delta E. And there we go. We can use that right there. So now it's just a matter of putting everything in there, and we'll have it in terms of meters. I'll show you how it's in meters here. So lambda is hc, so 6.626, 10 to the minus 34 joule seconds. We're going to have to multiply this by c, so that would be 2.997 times 10 to the 8th meters per second. And then we're going to divide that by our delta E, which is 550 times 10 to the minus 21 joules. Okay? So let's calculate that out and see what it is. 6.626 times 10 to the minus 34 times 2.9979 times 10 to the 8th divided by 550 times 10 to the minus 21. And it looks like it's minus 7. So it looks like it's 3.61 times 10 to the minus 7 meters. How is it meters? Joules cancel, seconds cancel, and you've just got meters right over here. Okay? So there it is in meters, but they want it in nanometers. So 1 nanometer is 10 to the minus 9 meters. So let's do our little conversion here. I guess I'll do it here. 3.61 times 10 to the minus 7 meters, and 1 nanometer is 1 times 10 to the minus 9 meters, and you get 361 nanometers. By the way, that's ultraviolet. Okay, there you go, 361 nanometers. So this is one in which they actually give you the energy levels on the axis there. So sometimes they don't give that to you. Sometimes you just have to say it's a hydrogen atom and then calculate 1, 2, 3. But for this one, we don't have to do that because they actually give us the energies there.